43rd lecture on the lecture series on nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. So today's speaker is Professor Tanmoy Banerjee from University of Burdwan, Department of Physics, University of Burdwan, West Bengal. And he is going to speak on a very interesting topic, nonlinear dynamics of dissipative systems, quantum dissipative systems. Before Professor Banerjee starts his lecture, so let me briefly introduce him. So Professor Banerjee obtained his PhD degree from the University of Burdwan, and he started his career in the year 2006 as an assistant professor in the Department of Physics. He works on many topics in nonlinear dynamics, including coupled map lattices, chaotic dynamical systems, nonlinear electronic circuits and systems, symmetry breaking in coupled oscillators, oscillation suppression in particular amplitude depth and oscillation depth, and the today's talk is nonlinear dynamics and quantum regime. He collaborates with many people all over India and as well as abroad. He has already guided several students and is now supervising a bunch of research scholars. He is serving as an editorial board member in Frontiers of Computational Neuroscience, Frontiers in Network Physiology, and Pramana, Journal of Physics. He is also a fellow of the Institute of Electronics and Telecommunication Engineers, India. He has been invited to give lectures on nonlinear dynamics at various meetings, both in this country and outside the country. He has also written an interesting book on time-delayed chaotic dynamical systems published by Springer. Professor Banerjee is a well-known person to our department. He has already visited our department in the year 2017, and he has collaborated with our faculty members. So I'm extremely happy that he is able to give a lecture in this lecture series at the Nonlinear Dynamics department. And with this short introduction, I'm now inviting Professor Tanmoy Banerjee to deliver his talk. So Professor Banerjee.
Thank you, Professor Lakshmanan, for your very generous and kind introduction. It's my honor to get introduced by such a pioneer in nonlinear dynamics, Professor Lakshmanan. And yes, I visited Bharathidasan University once, and it is like a mecca of nonlinear dynamics in India, if not in the world. So I convey my thanks to the organizers for having me. Good afternoon. Good afternoon to all the participants. To some of my collaborators, I can see Divakar. I don't know who else are there. So very good afternoon to all of them. Now, in this talk, I will be discussing a topic. The topic is how nonlinear dynamics is shaped in dissipative quantum systems, or what are the manifestations of nonlinear dynamical behaviors in the quantum regime. So that's why I have chosen this talk, nonlinear dynamics in dissipative quantum systems, and I will be discussing on mainly symmetry breaking, and other things I will discuss also later on. I will keep my talk very basic. Basic means I will keep my talk accessible to the students. So most of my slides are meant for them. Before I start, I must acknowledge my co-researchers, Vishwavivek Bandyopadhyay, Tania Khatun, and Dr. Devabrata Vishwas. Dr. Devabrata Vishwas is assistant professor in Bankura University, and Vishwavivek and Tania Khatun are working under my supervision right now for their PhD degree. Now let me start from very basic oscillators. So since we are nonlinear dynamical people, we are interested in oscillations. Oscillations mean for us limit cycle oscillations, chaotic oscillations, etc. And oscillators are everywhere in electronic circuit, biological systems, chemical reactions. We have some kind of oscillations, or some attributes of these systems are oscillating with time. So temporally, these systems are changing either periodically or chaotically. These are few examples of oscillators: human heart, chaotic circuit, this well-known BZ reaction, and predator prey, atomic oscillator, laser. So all these things are oscillators, and all the nonlinear oscillators are limit cycle oscillators. And in our textbook, we, especially in physics, we teach and learn harmonic oscillator, but unfortunately, an harmonic oscillator is not a so-called oscillator or limit cycle oscillator. Although it has a characteristic frequency, it does not have a characteristic amplitude. So harmonic oscillator cannot model all these things, that is our heart or predator prey model or electronic circuit, etc. So self-sustained oscillation or limit cycle oscillation needs some kind of special kind of treatment that considers both damping and pumping. And fortunately, Van der Pol in 20s proposed this particular form of oscillation or oscillator model. You can see that X double dot and X, these two things come from harmonic oscillator, and this is his contribution. And from this contribution, you can see that 1 minus x square, that is the term associated with x dot, is nonlinear. And if you closely look into the expression, you can see that there is some linear damping, linear pumping, and nonlinear damping. So pumping and nonlinear damping, this gives rise to a stable oscillation having a characteristic amplitude as well as characteristic frequency. So up to this point, it is clear that to get a self-sustained oscillator, limit cycle oscillator, as a kernel, we need harmonic oscillator. And with harmonic oscillator, if we introduce some kind of pumping and nonlinear damping, then we will get, or it is possible to get, limit cycle oscillation, which is self-sustained. Limit cycle oscillation, as we all know, it has a characteristic time period and also a characteristic amplitude. And more importantly, if a perturbation is exerted on such a system, they are not vulnerable to that perturbation. They can manage that perturbation. They will automatically come back to their normal behavior. So in phase space, an isolated closed trajectory, is the manifestation of limit cycle. Now come to the main topic of this talk. What is the manifestation of limit cycle oscillation in quantum systems? And number two, what is the quantum mechanical equivalence of VDP oscillator? So is there any quantum mechanical version of VDP oscillator? So that is the main question. What is our motivation? Why quantum systems deserve special attention? So why we are trying to exploring all these things which are well known in classical domain in quantum systems? There are two types of motivations. I have categorized them. Our academic motivation is this: in quantum systems, or all the quantum systems are inherently different from classical systems. Classical systems are manifested in macroscopic world, that is big systems or big scale system, I should say. In quantum systems, there are several constraints. For example, Heisenberg uncertainty principle that tells us that you cannot measure momentum and position of a particle simultaneously with a perfect precision. If you make a perfect measure of position, the momentum becomes uncertain, and vice versa. Similar is the case for energy and time. If you can, so momentum and position talks about, or Heisenberg uncertainty principle talks about the localization in space. Localization in time, that also is uncertain because of the fact that delta E and delta T, there is uncertainty in energy and uncertainty in time. Their product is not uh, 0 or 1. They have some kind of uncertainty. So there are several kind of uncertainties, and those uncertainties actually give the some fluctuations or noise. Those are called quantum noise. So in the presence of quantum noise, what will be the manifestation of, say, synchronization, oscillation, symmetry breaking states, etc. So all these things are uh, have to be discovered or have to be revisited separately for quantum systems. In quantum systems, there are dephasing, entanglement, quantum mechanical entanglement. These terms or these things are not associated with classical systems. So classical systems are free from these constraints like entanglement, dephasing, uncertainty principle, all these things. So quantum mechanical systems indeed deserve special attention. Apart from academic point of view, there are tremendous amount of applications such as quantum computing, quantum information, and quantum communication cryptography. All these are uh, coming edge applications of quantum techniques or quantum. Uh, so how could you map a particular quantum phenomenon into a particular quantum mechanical applications? That is a separate issue, that is a separate problem. So in a nutshell, we have sufficient applications of quantum mechanical systems, and for that we have to understand their behaviors. Now in this slide you can see that I have written the van der Pol oscillator in slightly different form. This is x double dot is equal to minus omega square x. This shaded region actually represents harmonic oscillator. And now I have added two different terms, A1 x dot, this is the pumping term, and this is the damping term. And you can see the damping term is nonlinear. You can see the x squared term, that is quadratic nonlinearity. So linear pumping and nonlinear damping are added in this harmonic oscillator, and we are getting van der Pol oscillator. This is the manifestation of phase space trajectory of this oscillator for K1 is equal to 0.2 and K1 is equal to 1 and K2 is equal to 0.2. And after writing amplitude equation of this particular van der Pol oscillator equation, we are getting this amplitude equation in terms of alpha. Alpha is a complex quantity. And for this, we use harmonic approximation. So under harmonic approximation, van der Pol oscillator reduces to our well-known Stewart-Landau oscillator, and this is the phase space representation or phase space trajectory, circular trajectory in real and imaginary alpha space. So this is our starting point. From this point, we will try to find out quantum mechanical version of van der Pol oscillator. Now, if you consider only the shaded region, this region, you can actually, we all have in our textbook the quantum master equation in terms of density matrix of harmonic oscillator. This is written in terms of A dagger and A, that is creation and annihilation operator, and the system obeys unitary operation. It has a perfect solution. This is quantum Lagrange equation. There is no twist in the story, but how to introduce this pumping term and this nonlinear damping term. And both pumping and damping are containing x dot, that is so-called the velocity term. So they cannot be accommodated in the Hamiltonian itself. So you have to add them separately. And to add them, you have to use the, say, you cannot use the unitary operation, which are well known in our quantum mechanics textbook. So in quantum mechanics, there is dissipation. Dissipations are inevitable in quantum systems. For example, optomechanics. In optomechanical oscillators, photon and phonon, they have some kind of damping. In superconducting circuits, ion traps, there are some kind of, in cavity quantum electrodynamics, there are some kind of loss of photon from this cavity. So in quantum optics, in general, if I say in quantum optics, dissipation comes due to the loss of photon from cavity or some kind of trap or some kind of circuits. So we have to consider dissipation in quantum systems. So harmonic oscillator in the presence of dissipation that cannot be managed by our so-called closed quantum mechanics. Up to our master degree, all the students know that in our syllabus, we have quantum mechanics. Those quantum mechanics is applicable for closed quantum systems. That is, the system does not interact with outer world dissipatively. But now we have a situation where we have an environment and we have a system. The system is interacting with the environment. And this interaction with the environment, all these things are the topic of open quantum system. And this is a very elegant book on the theory of open quantum systems. You can get some idea of open quantum system or the formalism of open quantum system here. And now this equation in the presence of dissipation looks like this. We have to write a Lagrangian, and we can get this quantum master equation after few approximations. There are three main approximations: Born approximation, Markov approximation. Markov approximation means environment does not remember the previous interactions, or in a simple term, quantum mechanical noise is Markovian noise, and also rotating wave approximation. So these approximations lead to these very simple, but not that simple, because Lagrangian is not that simple. I'm going into that. Now, quantum master equation for the van der Waals oscillator. This is called van der Waals oscillator in Lindblad form. It is some kind of phenomenological expression. And this expression, from this expression, you can see that this is the first part. The first part is for the harmonic approximation, harmonic oscillator. The second part, this is D called dissipator, Lindblad dissipator, and the operator form is this. D of a dagger, if you put a dagger in the place of O, you will get this particular term. So a dagger is creation operator. So this operator actually governs the creation of a single photon. So this is pumping or gain parameter. So pumping or gain parameter is controlled by this amplitude K1. And you can see D of A square. A is annihilation operator. So since you have A square, so two photons are being absorbed or annihilated. And from quantum optics, we know that two photon absorption process is a nonlinear process. The nonlinear process has an amplitude of K2. If you compare this particular equation with this quantum master equation for van der Waals oscillator, you can get the physical meaning of all these things. So this is pumping and this is nonlinear damping. This was reported in PRL in 2014. Lee and Sadekpour and the Bruder group. Almost simultaneously, they reported the quantum mechanical van der Waals oscillator and their synchronization. Now, the next question comes, how to visualize the oscillations, or what will be their manifestation. In classical system, we have some advantages. What are the advantages? We can visualize it in phase space. Suppose if I draw x versus x dot, I will get this particular phase trajectory. At the same time, I can also draw time versus x or time versus x dot. So we have both the components, that is, we can observe, we can uh, track the time variation of x, as well as we can observe it in phase space. But in the case of quantum system, there is no meaning of, say, tracking some, because A and A dagger are, they are not physical quantities, they are operators. If you track them in time, you will get nothing physical. So how to visualize the oscillation? And to visualize this oscillation, we have to use phase space in quantum mechanics. And phase space representation in quantum mechanics, there is this very powerful technique, powerful function, that is Wigner function. You can visualize it in phase space using Wigner distribution function, which is a quantum mechanical probability, or I should say quasi probability, because it can have a negative value also. So in phase space, you have to track the how Wigner function or Wigner distribution function behaves. So this is how you can track the behavior of the nonlinear dynamical behavior of quantum system. There are other functions also in phase space. For example, Hussein Q function. So those are the functions we will use in our study. So Wigner function, Hussein Q function, these are some quantum distribution function, probability or quasi-probability distribution functions. For example, this is a very popular picture taken from a paper that generates quantum mechanical superposition. So suppose this is dead state and this is alive state. So this is dead cat and this is alive cat. And due to quantum mechanical interference, you are getting an extra term, that is superposition of dead cat and alive cat. So quantum mechanics is actually weird. And you can see that this quantum mechanical interference in this portion, Wigner function becomes negative. So negative Wigner function means a true non-classical result. So this is the cat state. This is called cat state, quantum mechanical cat state. And this is how quantum limit cycle looks like. So this was our equation for quantum mechanical VDP oscillators. We simulate it, we numerically solve it. And for these parameters, K1 is equal to 1 and K2 is equal to 0.2 and omega is equal to 2. Omega is obviously the natural frequency of van der Waals oscillator. And we plot it. We plot the Wigner distribution function. Wigner distribution function in XY space. So real alpha and imaginary alpha space. And we are getting this kind of picture. This is in 2-dimensional and this is in 3-dimensional. Imaginary alpha, real alpha. And this is the Wigner distribution function. And you can see that we are not getting a ring, we are not getting a circle, but we are getting a spreaded ring. And I'm not showing the color bar actually, but believe me that this dark region has highest probability. The blue region has lowest probability. So what does it mean? It means that the system actually resides around this particular ring area. So instead of getting a circular trajectory, you are getting a spreaded ring. Here it is very obvious. So you are getting a spreaded ring. Here the probability is less. Here the probability is less, but here the probability is very high. So this is the difference between classical limit cycle and quantum limit cycle. In classical limit cycle, we get a circular, well-defined, prominent circular trajectory, but due to Heisenberg uncertainty principle, due to inherent quantum noise, we are not getting some prominent trajectory, but we are getting a spreaded ring. But this is not only the this is not the only difference between classical and quantum limit cycle. So this is our first point. There is no prominent phase trajectory for quantum limit cycle. The second part is that in classical phase trajectory, if you take a snapshot, then you can find that the system is localized. The phase point is localized somewhere. The phase point is moving through this locus, that is the phase trajectory, and the movement is in forward direction, in or the position of the point is changing with time. So if you take snapshot, after 1 second you will get here. After another time you can localize or you can observe the phase point here. So phase point is tractable or phase point is localized. But the most common feature of quantum mechanics is that systems are very hard to localize. Why? Because there are uncertainty principle. If you try to localize a system, you are making the position of the system fixed. So that's why its velocity become or its momentum becomes or fluctuation in momentum increases. So how quantum limit cycle evolves? In quantum limit cycle, if you start from this particular set of initial condition, this blob of sphere is called coherent state. If you start from this coherent state, after certain time, suppose t, this is the numerical simulation, t is equal to 3, you are seeing that, you can see that the blob is getting diffused, and as time passes, the diffusion becomes prominent, and after a certain time, after the transient passes, you can see that the system is residing in a ring, spreaded ring. Now, if you take a snapshot of this ring, you cannot get a particular point here, because now the system has finite probability of getting here and here and here over the ring. So there over the ring or around the ring, the probability of getting the system is equal. So unlike classical phase trajectory, the phase point is changing with time. We can say that quantum mechanical limit cycle is a true steady state. You cannot localize a particular point. And I can show you an animation. I started with this particular, let us start from beginning. You can see that this is the starting point. After that, the system evolves. And as it evolves, the initial coherent state is spreading over the ring, spreading over the ring in an uniform way. There is no way you can distinguish this part with this part. So the spreading is uniform around the ring. So if you take some snapshot, you will always get some uniform things that is localized along a particular ring. So in quantum mechanical limit cycle, it is a true steady state. And the third point is there are other several points, other several differences, but these are three very basic differences. Now, we know in classical limit cycle oscillation, the amplitude is bound, but phase is free. But in quantum mechanical system, quantum mechanical limit cycle, not only phase is free, but phase is indeterministic. You cannot determine the particular phase. So phase is not a very deterministic thing like classical system. Now, before I proceed, let me quickly discuss another important thing regarding quantum systems. There are two types of regime in quantum mechanics. First regime is weak quantum regime. In weak quantum regime, pumping is more than damping. Pumping is more than damping in weak quantum regime. So since pumping is more, you can see that the amplitude of the so-called quantum mechanical oscillation is larger than these. This is the, you can see that here K1 represents pumping and K2 is damping. So here pumping is less than damping. So this is called deep quantum region and this is called weak quantum region. If you consider Fock states, Fock number, that is distribution of photons or phonons and their probability corresponding occupation probability, you can see that this is the ground state. In weak quantum regime, the peak appears away from the ground state. But in deep quantum regime, maximum probability or maximum population or most populated state is the ground state. So in deep quantum regime, particles come towards the ground state, and in weak quantum regime, particles are far from, or the probability of getting the particles are higher in the higher energy states. So this is all about, not all about, this is in a nutshell actually. In a nutshell, what is quantum mechanical limit cycle and how they differ from classical, conventional classical limit cycle as we know. Now come to the collective behavior, because we are interested in synchronization, symmetry breaking, etc. And this is our motivation. This slide is for students, new students. Natural systems are rarely isolated, as we all know, and coupled systems behave differently than their constituent elements. This is called emergent or cooperative dynamics, so collective behavior. So coupled oscillators provide an useful paradigm for the study of collective behavior of complex systems. So to understand complex systems, we need to know the collective behavior of coupled oscillators. And couple oscillators show a plethora of complex collective behaviors. In weak or moderate coupling, we have synchronization, phase locking, etc. In the strong coupling condition, we have several others. For example, death state or oscillation death, amplitude death state, etc. And in between them, we have a regime of very interesting regime that is called the chimera states. So we have several manifestations of collective dynamics. We have synchronization, phase locking, chimera, other kind of symmetry breaking states of oscillation suppression states. Uh, Synchronization is these are the manifestation of synchronization. This is only for the new students. Fireflies in a bush or tree flies in unison in phase lock loops. Phase lock loops are some electronic devices, rather systems that are present in your mobile phone, in your laptop, in your computer. So in each mobile phone, you have a phase lock loop or several phase lock loops, laser, perfect balance or perfect synchronization of atomic uh, oscillators, Josephson junction, sound of crickets, clapping in social gatherings. So these are all the manifestations of synchronization among oscillators. Now the next natural question comes, how does synchronization occur in the quantum regime, or how does synchronization behave in quantum domain? And it is very natural to ask because since quantum systems have inherent quantum noise, the inherent quantum noise rooted from the Heisenberg uncertainty principle. So the question will be how synchronization phenomenon uh, manifests itself in the presence of quantum mechanical noise. And the answer is this: inherent noise in the quantum systems actually defies exact synchronization. And this was reported by Lee and Sadekpur and the Bruder group in December 13 and March 2014. So almost simultaneously, what they consider is this: they considered a quantum van der Pol oscillator, or you may now say it, quantum Stewart-Landau oscillator. In quantum mechanical literature, uh, quantum VDP oscillator and quantum Stewart-Landau oscillators are used interchangeably, although we know that they are not the same thing. So, but we will go according to the quantum mechanical literature. We have a quantum limit cycle oscillator. We have an external drive. We are driving with some amplitude and some frequency. This is the very basic setup, and this setup has already been explored in classical system in 1920s. But in 2013 or 2014, these authors tested the same in quantum domain. You can see that this particular driving, external driving, is manifested in the Hamiltonian. This is the driving force, IF A minus A dagger. And delta being the frequency difference between the single oscillator and driving oscillator. So omega minus omega d is the frequency difference. Now, if omega is equal to omega d, it is expected that they will synchronize. But in the classical domain, we know that even if omega is not equal to omega d, this is the flattest region, flat region. So in this flat region, in the presence of frequency difference, you can see that in classical system, both the system, that is driver and the slave, both have the same frequency, or frequency locking is possible. But in the quantum case, although it looks flat, but Bruder group, actually they zoom into the portion, and you can see that only at omega is equal to omega d, they synchronize, but as soon as they are different, synchronization is lost. So there is no plateau-like region, which is the characteristics of classical synchronization. There is no plateau-like region in quantum oscillator driven by an external signal. So all the studies in quantum synchronization, all the studies suggest that there is no strict frequency locking in quantum regime. And this is due to the fact that the inherent quantum noise defies the synchrony. There are some techniques proposed in the literature to improve the degree of synchronization by using, say, squeezing or other Carl nonlinearity, etc. I am not going into that part. Those are improvement of quantum synchronization using some techniques. The first experimental observation of quantum synchronization comes in 2020, and it is from our Indian group. Sai is there, Sai Viganampati, group of Shaikot Ghosh. And at the same time, this is a completely experimental study, but this is the study with IBM Q system. This is from the Bruder group. So in 2020, we got the first verification, experimental verification, observation of quantum synchronization. Now, what about symmetry breaking in coupled quantum oscillators? We know that there are two symmetry breaking states mainly in coupled oscillators. One is in the oscillatory state, we have the symmetry breaking in synchronization, I should say synchronization breaking, the coexistence of or incongruous coexistence of synchrony and asynchrony, which is popularly known as chimeras, and several people are there, including the group of Professor Lakshmanan, Divakar. They are doing great job in chimera states. This is the illustration, an illustration of chimera state. We have 200 oscillators. This is classical chimera states. I am not talking about quantum chimeras. I have 2,000 oscillators, and you can see that some of these oscillators are oscillating in coherent manner, synchronous manner, and these are oscillating in asynchronous or incoherent manner. So this is the incongruous coexistence of synchrony and asynchrony in symmetrically coupled identical oscillators. And it is believed that these chimera states has some relevance in explaining the, for example, unihemispheric slow wave sleep of migratory birds, uh, dolphins, etc. So now, what is the quantum mechanical manifestation of this very well known and very well derived? Uh, it has a very rich literature in classical domain, that is chimera state. So what is the quantum mechanical manifestation of chimera state? And it was first given by the Sol group in 2015. This is the classical chimera, and in classical chimera, this is the initial condition, that is t is equal to 0, and the right panel represents after some certain point t is equal to 0.5. Initially, they have chosen these initial conditions belong to the coherent state, and these initial conditions belong to the incoherent state, and these are Husserl Q functions. Husserl Q functions, you can see that there are circular states, and since all are represented by circle, and circle has no preferred direction, so they have no preferred directions. Number one. Number two, you can see that the points taken from the synchronous regime, they have almost the same direction. These are the arrows. They have almost the same directions, and point taken from the asynchronous region, they have different directions. That is synchrony and asynchrony in the initial condition. Now, as time passes, you can see that the circles are no longer circle, they are squeezed. These are called squeezed state. In the coherent states, the squeezing directions are identical. These are the squeezing directions. But in the incoherent state, the squeezing directions are not identical. They are randomly oriented. So this is they call the quantum signature of chimera state. So in quantum chimera states, means that the direction of squeezing that represents the notion of synchrony and asynchrony. If squeezing directions are same, they belong to the synchronous group, and if they are not, they belong to the asynchronous group. Another kind of symmetry breaking is this transition from, say, amplitude death to oscillation death. So amplitude death is a oscillation separate state. In oscillation separate state, if you choose proper coupling, it may happen that two oscillators interact with each other in such a way that they arrive at a common stable steady state. And in oscillation death, the oscillators populate different coupling dependent steady states. So oscillation death is symmetry breaking state. But amplitude death, you can say that symmetric state, because all the oscillators are arriving at the same steady state. Now we consider mean field diffusive coupling to explore or to discover how symmetry breaking should look like in quantum domain. And for that, we consider two mean field diffusive quantum van der Pol oscillators. uh, through diffusive mean field diffusive coupling. Why we choose mean field? Because it is a tested candidate for symmetry breaking in coupled oscillators in classical domain. You can see that this is the oscillatory state. As we increase the coupling constant, we are getting amplitude death, and after that, two oscillators populate two different steady states. So here symmetry is broken through pitchfork bifurcation. Now, what will be the manifestation of this particular interesting behavior in quantum domain? We transform this particular equation, this classical equation, into quantum masters equation. And in quantum masters equation, you can see some physically identifiable things or terms. This term actually represents a single photon loss. So you can say that since single photon loss is there, it is expected that uh, both the oscillators will go to steady state through this loss, because this loss is not managed by the the say original gain present in the system, that is governed by Q1. Now we numerically simulate this master's equation, quantum master equation. In the case of lower EPSA is equal to, that is coupling strength is very small. We are getting oscillations, limit cycle. And as we increase EPSA 5.75, we are getting amplitude death, quantum mechanical amplitude death. How can you recognize this amplitude death? Because you can see that there is the maximum probability appears at zero amplitude. But here maximum probability is around this ring, which is non-zero. From the Fock state itself, the distribution of Fock state also, you can understand that this is actually indeed a amplitude death, quantum amplitude death state. At EPSA is equal to 0.01, particles are scattered all over, but here particles are, most of the particles are populating the ground state. So in quantum domain, quantum amplitude death means the population of more and more population of ground state by tuning the coupling strength. So up to this point, it was okay that we are getting quantum amplitude death, but we were initially confused what should be the manifestation of quantum oscillation death state. And finally, we identified that in the case of oscillation death state, the Wigner distribution function shows a bimodal behavior. Bimodal behavior means we are getting two peaks separated from the zero, and these two peaks are unique in the sense that from the distribution of the elements of the density matrix, you can see that not only diagonal elements, we have off diagonal elements also, and off diagonal elements are actually the measure of quantum mechanical interference. So these peaks are coming due to quantum mechanical interaction between two oscillators, and we, apart from these two peaks, we have these interference terms also. So quantum oscillation depth is not just two peaks. It actually means more than that. And in quantum domain, we have quantum mechanical correlations also, which is not present in classical oscillation depth or classical symmetry breaking state. Okay, I'm skipping this. Now, our next question was, can we get some kind of some equivalent of Turing pattern or Turing type bifurcation? In macroscopic world, we have Turing patterns, but we are fortunate that in the setup of two oscillators, we still can have Turing patterns in the form of the transition from amplitude depth to oscillation depth. That is continuous transition from amplitude depth to oscillation depth. And this was the report where they called it a Turing type bifurcation. Although it is not an exact replica or exact representation of Turing type or Turing pattern or Turing bifurcation. So I will use the term Turing type bifurcation. So up to this point, we could not find direct transition from QAD to QOD, but again, from our insight and knowledge of classical nonlinear dynamics, we use conjugate coupling. We tried conjugate coupling in quantum van der Pol oscillators because conjugate coupling gives this AD to OD transition in quantum in classical domain, classical oscillators. This is the quantum master equation that represents two conjugately coupled van der Pol oscillators, or I should say quantum Stewart-Landau oscillators. You can see that as we increase coupling strength, the system at lower coupling strength, we have quantum mechanical oscillation. As we increase the coupling strength, we have squeezed amplitude depth state, that is quantum AD, quantum amplitude depth. And after that, we are getting bimodal Wigner function, that is the manifestation of quantum oscillation depth. And this we are getting continuously, that is the transition is continuous from QAD to QOD. And we call this Turing type bifurcation in quantum mechanical oscillators. This we confirm our result in noisy classical model using the formalism of Wigner function, Wigner distribution function. And in noisy classical model, you can see that the same scenario can be seen. That is, for at epsilon is equal to 1, lower coupling strength, we are getting some smeared ring. Smeared means since the system is noisy. Then at epsilon is equal to 1.3, we are getting some squeeze type of amplitude depth, and at 1.99, that is higher epsilon, we are getting two or bimodal, or the phase space is populated or maximally populated in these two regions. So our noisy classical model, this is analysis, this is simulation, and this is analysis with in the semi-classical regime. And this paper was published somewhere around August 2021. And just before that, we were very excited that our prediction was experimentally quantum mechanical Turing pattern was reported in the same year, nanoscale Turing patterns in a Bismuth monolayer, and they experimentally got quantum mechanical equivalent of Turing pattern. And finally, I will discuss our recent work. We have kept it in archive. Those who are interested, you can go through this paper. That is, Carr nonlinearity hinders symmetry breaking states of coupled quantum oscillators. So what will happen if we introduce Carr nonlinearity? Why nonlinearity is being introduced? Because in almost all the quantum systems, especially in quantum optics, Carr nonlinearity is inherent, almost inherent. So what will happen in the presence of Carr nonlinearity? That was our intention to explore. The van der Waals oscillator remains the same, except the fact that now Hamiltonian contains not only omega Edgar, but it has a Carr parameter k of Edgar whole square. So we have a Carr nonlinearity in the Hamiltonian, and this particular term we have observed that drastically changes the symmetry breaking landscape. The k is the Carr parameter, k versus EFSA. You can see that if k is equal to 0, the system is in symmetry breaking state, quantum OD state. If we increase the Carr parameter after certain value, the quantum OD state, that is symmetry breaking state, is lost, and we are getting a perfect symmetric result, that is quantum amplitude depth. So the presence of Carr nonlinearity actually destroys the symmetry breaking state, and it brings the system to a more symmetric state. This is the quantum chimera. We show here 49 oscillators. In this bracket, all these oscillators have the same, you can see they have identical Husserl function distribution, but these oscillators from 22 to 49, they are oriented randomly. So these are forming the asynchronous or incoherent group, and these are the coherent group. So this is in the absence of Carr nonlinearity. If we introduce Carr nonlinearity for illustration purpose, exemplary value k is equal to 1 is taken, and you can see that all the oscillators have the same phase. Same phase means indeterministic phase. That is, the phase are now not recognizable from each other. So they are symmetric. So Carr nonlinearity in the case of chimera also, Carr nonlinearity destroys chimera state and impose more symmetric oscillatory state. So this is all about my talk, and there are several open challenges. The field is very new, and field is, I should say, dominated by the people from quantum optics. So there is a problem of language of nonlinear dynamics often does not match with the language of quantum optics. This is our first challenge. The second challenge is, as I have discussed, nonlinear dynamics in the quantum regime depicts several interesting results, and we should study the classical counterparts in the quantum regime. But the challenging part is this: the extension of the techniques used in the so-called classical nonlinear dynamics. You cannot just use all those things and bring all the result to quantum domain, because there is no exact straightforward technique such that you can uh, take a classical system and convert it into quantum mechanical quantum master equation, then simulate all these things. There is no such thing exists till date. So going from classical to quantum model is non-trivial and thus very much challenging. There are other challenges too. Challenges come from the computation point of view, because some wise men already said that quantum mechanical simulation requires quantum mechanical quantum computers. So Feynman was true, because we are facing this problem. If you have n number of nodes, your Hilbert space will become 2 to the power n. So and quantum mechanics lives in Hilbert space. So if you want to explore your ideas in network, it is very uh, difficult computationally. So it will take much time, and it is advisable to simulate a quantum system in quantum computer, and which is very uh, not. It is not that we all have quantum computers in our lab. And the final part is the inherent ideas of quantum mechanics, such as entanglement, dephasing. These things are needed to be connected with synchronization and symmetry breaking, and much work is needed in this direction. So that's all. Thank you all.
Okay. So thank you very much, Dr. Tanmoy Banerjee, for a very beautiful and scintillating talk. We really enjoyed it very much. And now the forum is open for questions. So I see already one hand raised, Chitika Ruby. Chitika.
Sir, Chitika. Sir, I like to understand how you have written that master equation for the coupled oscillator, and each oscillator is how you have taken care of the damping. How you consider that each oscillator is coupling to that environment, as well as both are interacted with each other. Is it so, sir?
Okay. So the first part of your question is very non-trivial. As I said, there is no clear technique. That is, I cannot say that you just go in this way and you will ultimately arrive into the master equation. But the starting point is this. Let me show you. The starting point is this. If you have amplitude equation, from this amplitude equation, this alpha is nothing but the average value of annihilation operator. So from that, using tie-and error method, I am using the term tie-and error method because till date, no exact technique of quantization. Quantization means if you have this particular equation, if you quantize this equation, you should get its quantum version. But till date, we don't have any technique, quantization technique, such that you will get some quantum master equation or some kind of all those things. But starting point should be this. If you can write down in amplitude equation, and alpha is nothing but the average value of annihilation operator, then you have to proceed. This is the first part. And second part, you actually don't have to consider the interaction with environment, because since we are using Lindblad dissipator, in Lindblad dissipator, these thing arrives after eliminating all those parameters for all those effects of environment using these three approximations. So don't bother about environment, use Lindblad dissipator. But the first part I cannot help you. There is no clear-cut technique of getting master equation.
And one more question, sir. That input state you have considered as a coherent state, sir. Why is it so, sir?
Okay, okay. Good question. In the case of classical system, we generally take a non-zero value of x and x dot. If it starts from zero, it remains there. If zero is a steady state, trivial steady state. Here, uh, coherent state is actually the you can say non-zero value in the phase space of quantum or quantum phase space. So in quantum phase space, a non-zero value, a point having non-zero value is the coherent state. That is uh, off from the or far from the origin.
Thank you, sir. I'm having one more question, sir. Sorry. And that finally you have discussed about the Kerr nonlinearity, that Van der Pol oscillator along with Kerr nonlinearity. And that Hamiltonian, the Kerr nonlinearity only because of that, as you said, that master equation, Lindbladian operator you have considered, that is why you have considered only that Kerr nonlinearity in the along with that Hamiltonian. It means that you are considering a nonlinear Hamiltonian. Is it so, sir? That
Yes,
it
yes,
doesn't it doesn't participate in that yeah, other two parts, that pumping as well as the dissipation one, sir.
yeah. Dissipator part is not changing.
Yes. So how one can understand that Kerr nonlinearity along with that Hamiltonian, original
Okay.
Hamiltonian?
If you think classically, you can say or you can think like this. Suppose you have an equation x double dot plus bx dot plus omega square x, okay, is equal to 0. It's a damped harmonic oscillator. Now, if you add excess q, suppose, that excess q will affect the omega square x part, that is omega square x plus excess q. It does not affect the x dot part, that is uh, the damping part.
Thank you, sir.
Okay. Any other questions, comments? Anybody? Tanmoy, I have a few questions.
Yes, sir.
Yeah. The amplitude equations you deduce for the quantum van der Pol oscillator is under harmonic approximation.
Yes, sir.
So how good is this approximation? And if you go beyond this harmonic approximation, what happens?
Actually, uh, there are actually two papers there just published in 2020. They used relaxation oscillator, Van der Pol oscillator. They did not use the harmonic approximation. And in those papers, they showed that if harmonic approximations is not considered, then there will be some uh, will be some modifications in the Hamiltonian itself.
Yes.
And the thing is not very much trivial because they have to consider all the terms in the oscillator, and they have to quantize those terms and get the final form of the quantum master equation.
Yes.
So the relaxation oscillation in quantum mechanics is the work has just been started with those two papers, and those are still challenging.
Yeah. So that means, I mean, there is every possibility of getting a better quantum mechanical formulation of these amplitude equations, and yeah, the results may change. Yeah, I have one more question. You have severe ordering problem. I mean, when you introduce uh, quantum damping, in particular position dependent damping,
Mm.
x square x dot, for example.
Mm.
So that when you go to quantum mechanics, it's going to introduce severe ordering problem. So
Yeah.
that you see, you do not seem to have taken care of. So what will happen if you try to introduce better ordering of the initial equations? How do your results will change
Mhm.
in the quantum case?
Actually, conventionally, all are using a particular ordering,
Yeah,
symmetric
but
ordering.
yeah, but when you go to class quantum mechanics, so that's not
Mhm.
all correct.
I understand.
The simplest ordering, for example, you can, well, if you have x square p, you can write as x half of x square p plus p of x
Mhm.
square or something like that. But x dot is much more involved.
Yeah.
So I do not know what is the effect of ordering will be. So
Mhm.
I think there is an interesting problem to be studied there by at least simplest ordering. One
Mhm.
can try to incorporate and then see what is the end result.
It's a very important problem actually in the context of nonlinear quantum oscillators.
Yeah.
Yeah.
So yeah, that you can try to think of that.
Mm.
I have also one question. You said that quantum mechanical limit cycle is a true steady state. But in classical mechanics also it's a true steady state. So
No,
what is the
in
distinction between
yeah, yeah.
classical and quantum
Uh,
mechanics?
what I mean by steady state is that in classical mechanics, you can actually localize the phase point. If you take the phase point at different time, you will get different positions.
Yeah.
But in quantum mechanics, you will not able to get a particular localized point in the ring. The system is
In
situated,
there, the point.
yeah,
Yes.
the probability is the same along the ring.
Okay.
That's why I use the term true steady state.
Okay. Good.
It's not changing with time.
So any other questions, remarks anybody wants to make? Yeah, I don't see any further questions. If not, let us thank Professor Tanmoy Banerjee for giving a very beautiful and stimulating talk in this lecture program. So thank you very much, Tanmoy. So hope to see
Thank you,
you
sir. Thank you.
in future.
Thank you.
Okay, all the best, and then yeah, goodbye. Goodbye.
Bye, sir.
Okay, thank you.